All right, in 5.3, it says to solve trigonometric equations, we use standard algebraic techniques such as collecting like terms and factoring. The initial goal is to isolate the trigonometric function. So what we're going to do is we are going to add 1 and divide by 2. If it bothers you solving trig equations, like it just seems too confusing with the trig function in there, a suggestion would be to use U-Substitution. And so you would have 2u minus 1 equals 0. And then back substitute. So we're still going to get to the same place. But again, if it bothers you with the trig, then use that instead. All right, now, when I see sine x equals 1/2, some of you have been too dependent on your unit circle paper. And I want you to try to do this without using that paper. Learn how to do it without it. That was to get it in our heads. And now we want to try to go on without it. Say goodbye to it. Okay. Goodbye, unit circle paper. All right. If I have sine x equals 1/2, in what two quadrants is the sine function positive? All right. First of all, we know it's in the first and the second quadrants. The second thing we should know is the reference angle. Now, if you need to, you can draw 2 little triangles, but I don't want you using that whole circle anymore. If this is a 45, 45, okay. So, what is the reference angle for sine x equals 1/2? Pi over 6. And I love it that you answered in radians. It's 30 degrees, but that's pi over 6. So then, I'm in the first and the second quadrant. That's pi over 6 and 5 pi over 6. Now, this does not say solve it over the interval from 0 to 2 pi. It says solve it. So that means we have to revisit something.
No.
Your favorite. This did not go away. And if it does not give you an interval, that means you have to do it in general. So if you struggled last chapter, we're going to get it. We are really going to get this. Notice that the distance between pi over 6 and 5 pi over 6 is 4 pi over 6, but that adding another 4 pi over 6 would not roll me around to the first quadrant. So it's just going to be pi over 6 and then add a whole one, and you're at 5 pi over 6, add 2 pi, add 2 pi, okay? We'll see some other ones, but... Okay, example 2. It says solve sine x plus square root 2 equals negative sine x. So I'm going to start by subtracting sine x from both sides of the equation, and I get radical 2 equals minus 2 sine x. Divide by negative 2, and I get sine x equals negative radical 2 over 2. All students take calculus. In what two quadrants is the sine function negative? Third and fourth. And we ought to know the reference angle on this one. What's the reference angle for radical 2 over 2? Pi over 4. Good. So x is 5 pi over 4 and 7 pi over 4. Now when you write it in general, it's not always going to be plus 2 pi n. These first two were. And I suppose this is not the greatest advice, but when in doubt, add 2 pi n. You got maybe a 50-50 shot at it.
I like those odds.
Yeah. Not the greatest advice. advice I can give you, but at least it would give you something to write down. So if you look at it, like I can't add, if I try to add 2 pi over 4 or pi over 2, if I add another pi over 2, I'm in the first quadrant. There's not a first quadrant value. All right, so let's move on so we can see another solution that might be a little bit more interesting. In this one, I'm going to start by adding 1. I'm going to divide by 3. Now, be very, very careful. When you have something squared, you've got to remember that it's the plus or minus square root. So this is tangent x equals plus or minus, the square root of 1 is 1, the square root of 3 is 3. That's plus or minus the square root 3 over 3. So, all students take calculus. Tangents positive and negative. Do you understand that's all 4 quadrants? And then what's my reference angle?
Pi over 6.
Pi over 6. Good job. So now I need all 4 pi over 6 angles. It's pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. There are not 4 answers this time. It's not each of them plus 2 pi n. There is a way to condense this. I will tell you there's 2 rows. Tyler, what do you think?
I think there's 2.
There's 2.
Never mind.
Okay. No. There's 2 rows to the general solution. Anybody want to try it? Sophia, you want to try it? No. No? Okay. Josh, what do you think?
Pi over 6 plus pi and 5 pi over 6 plus pi?
Yes, it is. Good job, Josh. And let's look at why that is. Let's write it down. All right, if you initially think about this, okay, the distance between these two, or the difference between them, is 4 pi over 6. But if I try to add 4 pi over 6 to that one, it's not 9 pi over 6. It was 7 pi over 6. So that doesn't work. So then what you want to do is you want to look at every other one. This has a distance, or difference, of 6 pi over 6, which is pi. And think of it like this, okay? Here's pi over 6. Here's 7 pi over 6. Do you see that has a distance of pi? So to get around is another pi to another pi to another pi and another pi, like that. Likewise, going around the 5 pi over 6's. Okay? All right, what I want you to do is I want you to take out the worksheet packet I gave you, and we're going to do one of the homework problems. I want you to do number 1. Don't move ahead of that one because we haven't reviewed the other types. But I want you to pull out that homework, and I want you to try number 1. It is a secant, so I want you guys to try this, but you really do have the tools in your tool belt. Now there's more than one way to do this one, but when you get to this point, secant squared x equals 4/3. Here's how I like to do it. I know that secant squared x is 1 over cosine squared x. If you have one fraction equals one fraction, you may flip both fractions. So then cosine x is equal to plus or minus radical 3 over 2. So this is all 4 quadrants. all students take calculus. It's in all four. What's the reference angle?
Pi over 6.
Pi over 6. Isn't this the exact same as example 3? Now? Actually it is. So you'll notice there is a limit to the number of answers you can get. So I'm getting x equals pi over 6 plus pi n, where n is an integer. X is 5 pi over 6 plus pi n. Now, if you write down 4 of these with plus 2 pi n, you'll lose points because that was not the most efficient way to write the general solution. Okay, so be careful. You did not have to go this route. If you can handle secant, and you know secant's hypotenuse over adjacent, you can go that route. That's okay too. All right, back to our notes. The equations in examples 1, 2, and 3 involved only one trigonometric function. When 2 or more functions occur in the same equation, collect all terms on one side and try to separate the functions by factoring or using appropriate identities. So in example 4, I notice I have cosine and cotangent. So I need to get everything on one side of the equation equal to 0. And what's really cool is that if you remember all the way back to Algebra 1, that's such a long time ago now for us, but we had something called the zero factor property that said if A times B equals 0, then A is 0 or B is 0. We're going to use that same property, but use it at a much more advanced level with trigonometric functions. So on the left side, do you see there's a GCF of cotangent x? So I get cotangent x times the quantity cosine squared x minus 2 equals 0. So the zero factor property says I set each factor that contains a variable equal to 0. So cotangent x equals 0, or cosine squared x minus 2 equals 0. Well, when I look at cotangent x, what I know is cotangent is cosine over sine. And I need to look at the 4 values on a unit circle. And I'm looking at where I would have 0 over a number, where cosine is 0. Well, it goes cosine comma sine, so that's occurring at pi over 2, and it occurs at 3 pi over 2, because it's 0 over 1 is 0, 0 divided by negative 1 is 0. So I've got those two. Now let's come over here, and I have cosine squared x equals 2. Cosine x is plus or minus the square root of 2. Well, what do you know about the square root of 2? Approximately what is it? Without a calculator. Okay, not a bad guess. It's 1.4-ish, but we know it's bigger than 1, right? Now, do you remember from the cosine graph, the cosine oscillates between what two numbers? 1 and negative 1. So you can't get a 1.4 out, or something bigger than 1. So this piece does not produce a solution for us. Now, let's try to write this in a general form. Pi over 2 and 3 pi over 2. Tyler, what do you think?
I have pi over 2 plus pi and is an element of the integers.
Okay. Now, if you notice that there's a difference between these, and that if you add that, it would get you right back to where you want it to be, then that's when you can condense it down. Okay, this has a difference of pi, and if I add another pi, I'd be back up here and add another pi, add another pi. So that'll do the job for us. right, equations of quadratic type. 2 sine squared x minus 1 equals 0 is a quadratic type for trigonometric functions, as well as secant squared x minus 3 secant x minus 2 equals 0. The good news in example 5 is this says on the interval from 0 to 2 pi, so we don't have to write out the general solution. So what we're going to do is we're going to try to factor this. And what I mentioned on the previous problem, if it bothers you with the trig functions, you can use a U-Substitution. If I let u equal sine x, then this would be 2u squared minus u minus 1 equals 0. Factor it. And then you would just put your signs back in, okay? So not a problem. And that's only meant if you need that, okay? So then I have it factored. So 2 sine x plus 1 equals 0, or sine x minus 1 equals 0. I subtract 1 and divide by 2. All students take calculus. This will be the third and the fourth quadrant. I have a reference angle of pi over 6. So x is 7 pi over 6 and 11 pi over 6. Sine x equals 1. That's on my circle. And that's pi over 2. So there are 3 answers from 0 to 2 pi. So be careful on your homework, on the next quiz, and on the next test. If it just says solve, it's assumed you're going to give me the general solution. You'll lose points if you leave it like that. But if it does say over the interval 0 to 2 pi, you just need to list the ones from 0 to 2 pi. So be careful. All right, example 6 says solve 2 sine squared x plus 3 cosine x minus 3 equals 0. All right, we have a problem here because if I try to put sine x and I do an outer and an inner, the outer and inner are sine x, right? And I don't have a cosine x. All right, so what could we do? Tyler?
You could use the Pythagorean identity to change sine squared x into 1 minus cosine squared x.
There you go. Okay, so those identities don't go away. We're going to keep using them. So we need to put them all in terms of the same trig function. Because I didn't have a GCF or anything like that where I could factor it. All right, so this gives me 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. I have some like terms. And when we did this, when you did it in Algebra 1 and we did it in Algebra 2, when your leading term is negative, you need to change it to positive. And you can do that one of 2 ways. You either move everything to the right side, and it'll make it positive, you'll flip that sign, or just multiply both sides by a -1. Either way you want to work it is fine. I just multiplied both sides by a -1. Now we're going to factor. I get 2 cosine x. This is a 1, a 1. It ends with a plus, so they both have to be the same sign. So I get 2 cosine x minus 1 equals 0, or cosine x minus 1 equals 0. I'm going to give you a head start, and I want you to finish it. And this one did not say on the interval from 0 to 2 pi, so it's implied you're doing the general solution. you're a fast worker, while we're waiting, you can use that worksheet and work a couple other problems out. Be a multitasker. All right, let's look at this together. You get cosine x equals 1/2. So theta prime is pi over 3. So that's pi over 3 and 5, pi over 3. So if you look at this on a coordinate grid, there's no way to keep adding the same thing to get back around and around, okay, from the one to the other. So when that happens, you're just adding plus 2 pi n, okay? Then on this one, cosine x equals 1, that happens at 0 and 2 pi, so you can just do 2 pi n. That'll take care of that. Any questions on that one? Nope? Okay. All right. Example 7, this was as far as I wanted to get today, so we're going to do 7 with the exploration, then we'll stop there, and you could probably work on a few other problems. All right, example 7 says find all solutions of cosine x plus 1 equals sine x in the interval from 0 to 2 pi. Now this is not a typo. There's a parenthesis at the 2 pi. Okay, that means it's not included. Something I want to point out before we get going, we talked about this before. In the Pythagorean identity, sine squared x plus cosine squared x equals 1. That's true. But you may not individually do square roots. Sine x plus cosine x is not equal to 1 in general. That's not true. Okay, so I have no substitutions that I can do here. So I need to introduce a technique that you can use, and we actually used it in Algebra 2, and it's called the squaring property. So when you can't factor or substitute or isolate, you can use the squaring property. And what I want to show you is when we started with like the square root of x equals 3, we would square both sides like that, right? Okay? But the danger with it is that if I started with x equals 4 and I square, you can sometimes generate an extraneous solution. So that's why when we did our radical equations in Algebra 2, we needed to check them because you could generate an extraneous solution. So watch what I'm going to do with this equation. I'm going to use the squaring property to square both sides, but when I use this technique, I've got to check for extraneous solutions. So this is cosine x plus 1 times cosine x plus 1. And on the right side, sine x times sine x is sine squared x. On the left side, I get cosine squared x plus 2 cosine x plus 1. And then this reminds me of problem 6, just the one before, where they're not in terms of the same trig function. So we're going to use the same strategy here, where we're going to use a Pythagorean identity, and we're going to replace the right side with 1 minus, not sine squared, sorry, 1 minus cosine squared x. Now it's all in terms of cosines. So I'm going to subtract 1 from both sides, and I'm going to add a cosine squared x to both sides. So that's 2 cosine squared x plus 2 cosine x equals 0, because the 1's cancel. Now I want to try to factor it. What's step 1 in factoring? GCF. So there is a GCF. I get 2 cosine x times cosine x plus 1 equals 0. And if you can do this in your head now that you're sort of getting the hang of it, I'm getting cosine x equals 0 because the 2 would divide out, right? And I can get cosine x equals negative 1. This occurs at pi over 2 and 3 pi over 2. X is negative 1 at pi. Now, what I just told you before we started this problem was that when you do the squaring property, you have to check your solutions. So let's check each one. So you check it in the original equation. So I want to know, is the cosine of pi over 2 plus 1 equal to the sine of pi over 2? Well, this is 0 plus 1 equals 1, so that one works. Yes.
Why are we checking 3 pi over 2 if it's outside of our, never mind.
Yeah. 3 pi over 2 is inside 0 to 2 pi. Yeah, it's okay. All right, so this is 0 plus 1, but what's the sine of 3 pi over 2? It's negative 1. That one doesn't work. And that one does work. So be careful with the technique of squaring both sides, that you do have to check it. Now, what I want us to do is, it says you can graph the left side and right side if you're allowed to use your calculator, like if that's a viable option. Take out your calculators and let's go to our Y screen. And I want you to enter cosine x plus 1 on the right side, sine x on the left side, and we're going to graph it and look for the intersections. Now, because this is 0 to 2 pi, let's check our mode and make sure that we're in radians. And then the next thing we want to do is, you don't want to press zoom trig on this one, because zoom trig's going to go negative 2 pi to 2 pi. And we only want 0 to 2 pi. X scale, I mean, you could leave it as 1, but that's not as interesting in trig stuff. Let's make it pi over 2. And then Y, I'm not sure how much I'm going to need, so let's do negative 5 to 5, and then we can wiggle it some more if we need to. And then press graph. Notice there's two solutions, and when we checked it algebraically, we got two solutions. Now they're where they intersect. So press second, trace, intersect. And if I do this one that I'm near, notice we got pi was 3.14. Now let's go get this one. Second, trace, 5. You can do enter, enter, but when there's more than one intersection on the guess, you've got to move it towards the one that you want. And you get 1.57, which is about pi over 2, right? Now, this was one way where you can enter the left side and right side and find their intersection. The other strategy is you could get everything on one side equal to 0 and then find the x-intercept, or the zeros, okay? Which you would find by doing second trace and 0. Okay?